Now we have Brian, who will be talking about experimental quantum gravity with the B-step CMB polarimeter.
So I'd like to first start off by thanking the 33% of remaining conference organizers, namely Sydney, for making such an interesting and stimulating conference. So my job today is to put the E in ESQG, at least from the perspective of showing shiny pieces of metal and circuit boards and things like that. So I've paired with a lot of your guys' talks, which have been excellent, with your theory and math and everything, and those have been wonderful and informative and inspirational. But I'm going to talk a lot about experiments today. But there'll be a lot of theory in there too. Hopefully you guys can answer some of my questions. So BICEP is the name of a cosmic microwave background polarimeter, which my colleagues and I built at the South Pole in Antarctica. I'm going to be talking about the data, show you a little bit about what the experiment looks like, how it works, and in particular what makes it unique and so powerful for looking for the signature of inflationary generated gravitational waves. And BICEP was the first experiment ever designed to do this, to go after these gravitational waves from inflation. So it shares that distinction, and in doing so, we had to design it to be particularly clean and free of systematic effects, and I'll talk about the design motivations as well. But actually, what I want to talk about is not our main motivation with BICEP, which was to measure the gravitational wave background, but instead I want to talk about physics beyond the standard model. Something more interesting, perhaps. So this is a cartoon of physics beyond the gut scale. So the gut scale is hypothesized to be the scale on which inflationary gravitational waves will be generated. So here's a guy's gut scale. And you see, importantly, there's a systematic bias where she's putting the pen and where his gut has gotten to. Normally these things go upwards. This is going sideways. So the outline of today's talk is I'm going to talk about CMB polarization, give a brief overview. Luckily, Joao gave a brief prelude to this on the whiteboard the other day, and I can go quickly through that. Next, I'm going to talk about the prediction motivated by models of parity violation in the electromagnetic sector, of parity violation effects that could manifest themselves in the CMB. Why is the CMB important? Well, it's the oldest light in the universe. It was produced 400,000 years after the Big Bang. And it's traveled through the whole extent of cosmic history to us today for us to observe. So that means that there's a slight amount of birefringence in the universe that will accumulate over this fantastically long optical path length, and we'll be able to see that potentially as a measurable signal. In fact, somebody claimed using our data, not our team, but claimed using our data, this group led by Jia in China, or he's actually in Italy now, I believe. Using our data, which we made public, as I said yesterday, we're moving to the field, in the field to publicize our data, make full covariance matrices available. And they took our data and they used it against us. They claimed a 3 sigma detection of parity violation in the electromagnetic sector. Okay, so that's pretty startling, and it took us by surprise. Because 3 sigma in cosmology is pretty darn good. But as somebody said, 90% of all 3 sigma detections are wrong, and I'll tell you today some more evidence to advance that last assertion. Okay, I'll talk a little bit about our instrument, and then I'll talk about future upgrades to this type of experimental search in the CMB. Okay, first a brief overview of what polarization is. Polarization, you have an electromagnetic wave. It has 4 independent parameters, 2 amplitudes, 2 phases. Combinations of those we create as our observables in the CMB. Those are the Stokes parameters, IQ, U, and V. V is circular polarization, which will come into play, but of course we know we can decompose linear polarization into counter-rotating circular polarization with fixed phase. We don't believe that there's any circular polarization intrinsic in the CMB, although Stefan and others have made predictions, Kozowski, that there may be circular polarization arising from magnetic fields, primordial magnetic fields, and perhaps from the types of gravitational effects that Joao spoke about, and work that Stefan is also working on, and Lee Smolin and others. Okay, so we're just going to restrict ourselves to IQ and U because those are the only polarization terms that arise during Thomson scattering of unpolarized radiation off of free electrons, which there were copious amounts of both in the very early universe. And just for fun, I show here Q. What Q greater than 0 by convention is like this. This is a negative Q. Okay, So these are perpendicular to each other, but are actually not zero, the dot product of these in some abstract inner product space. But here, Q is 0 and U is greater than 0, and so on. Now, Q and U depend on the coordinate system. If you tilt your head, you can turn Q into U, or vice versa. So that's unpleasant. And that's a feature that circular polarization doesn't share. You can turn your head all you like, but circular polarization is still left or right-handed, independent of it. So about 10 years ago, several groups came up with the idea that they could synthesize a term not unlike circular polarization, which is roughly X polarization plus I times Y polarization, or minus Y polarization. They synthesize something that's essentially Q plus or minus IU. And they call these E or B types of polarization. And here's what they look like. Okay, this is what the amplitude of these things look like. These are not vectors. These are pseudo-vectors. They're headless sticks. So if you looked out in the sky, or anywhere, any polarization pattern, and you saw a pattern where all the polarization sticks were radially oriented away from you, that would be called a hot spot, an E hot spot. This would be a cold spot, negative Q, or this is positive Q, this is negative Q. That sign ambiguity is fine. And then if you superimpose many of these modes, this is just what a single point source would look like, you could get patterns that look like this. This would be a pure E mode, which when you decompose things in Fourier space, you would say this map is pure E, this map is pure B, and you see the difference between the two of these. This respects parity inversion. If you reflect across any line here, you get the same pattern here or here. Here you get a negative sign. So in analogy to electromagnetism, we say this is an E mode, electric mode, this is a B mode, magnetic mode, or respectively grad and curl mode. Because this is sort of like the gradient of a scalar field, and this is kind of like the curl of a vector field. Okay, and this also has that pattern. If you draw specific planes, you can reflect across and you'll get the opposite sign. Okay, so we call these E and B modes, when we make maps of the CMB sky, decompose them in Fourier terms, and make power spectrum. Power spectrum, not of Q and U, but of E and B. Those are independent of coordinate system. Okay? Now, the key is, this is a map on the sky of a stochastic superposition of many modes that only contain E mode content. And this is B mode. Now, I can't tell the difference between the two of these, and neither can you. So what we do with these types of patterns is we statistically decompose these. This has no noise added to it. Imagine adding noise to it, and it would be essentially impossible to reconstruct these just by eye. So what we do is we decompose this map, we make a map, we turn it into Fourier space, we look for modes of I times U plus Q, or minus I times U plus Q, and we decompose this field in that basis. Okay? And then we can extract the E and D components. And I'll show you maps of E and D later on in the talk. Okay? So the whole idea is that these are now, we turn a vector problem into two scalars. We turn Q and U, or the polarization vector amplitude and orientation, which is pseudo-vector, we turn that into E and D. So two scalar fields on the sky, not unlike temperature. It makes it very easy to do things like power spectra after that point. Okay? And this is a big breakthrough, and people wonder why it took so long, but for what it's worth, it was realized in '96 that you could do this. Okay? If you take maps of E and D, and you decompose them in Fourier space, you make power spectra. This is a canonical power spectrum. This is just of the EE modes, okay, shown here. And I'm only showing detections with greater than 2 sigma significance in multipole space. So each one of these multipole bins describes a 2 sigma detection. Here's the scale. This is in microkelvin squared. So this is 1 microkelvin on the sky. Okay? So less than a few parts in 10 to the 5th of the CMB background. Okay? Or 10 to the 6th. So this is microdegrees Kelvin. Okay? And these are the plots. You see the similar kind of behavior, the phenomena of acoustic oscillations, because polarization is driven by anisotropic photon distribution, as seen from the rest frame of free electrons. As I said, there are plenty of each of those at recombination. And so you get a polarization pattern in the E mode, which shares much of the physics with the temperature mode as well. You don't get extra information from just this plot alone. But it's a confirmation of the inflationary paradigm. See, is that guy, is it Nick who's here yesterday who's giving me a hard time? Okay. I don't see him, but maybe he'll show up to throw some tomatoes. Instead, what we measured for the first time with BISUP, or these plots here, these points here, we made the first detection of this peak, the first acoustic peak, which is super horizon size. So the horizon is L of about 180 or 200. This is approximately where the full moon is, a half a degree. Okay, it's L about 400. So this is on the sky. This is increasing angular frequency or decreasing angular size. And this is the full sky over here. Okay? So these are all the different detections that we made. We made this detection of this peak, which gives credence to the inflationary cosmology because there's no way to set down perturbations coherently across the whole sky unless you have your own favorite artificial or ad hoc model, and that's fine, but that are super horizons that are coherent over the whole sky as well. Now, the purpose of BICEP, you have driven Sabine out. She doesn't like the inflationary model. Okay, now the purpose of BICEP was to measure the gravitational wave background. Of course, it's something we don't know if it exists. We don't know its amplitude if it does exist. So we built what we thought would be the best telescope to go after it in the event that it does exist. Okay? And in the event that it had an amplitude which is lower than that was constrained before we built BICEP. So several of these experiments had existed before BICEP. DAISY are these very light blue curves up here. They made limits on the B modes. But you see this tremendous gap. Okay, so DAISY released their data on detection of polarization in 2002, 2003. Okay? So they released it here. So we're already more than 2 orders of magnitude down in the BB power spectrum in just 6 years. This is only 2 years of our data. We have 3. But actually, we had much greater observing efficiency in the last year or so. This data will come down. These are upper limits. These are all 95% confidence upper limits. So BICEP sets the tightest limit, and here's what the gravitational wave background would look like, the amplitude, in B-mode power spectra, if the tensor-to-scalar ratio was about 10%. This is the amplitude of tensor perturbations, the amplitude of scalar perturbations in temperature units. Okay? But if you like, this is the canonical parameter that we use to describe both the strength of the gravitational wave background and correlate it to the energy scale of inflation. Yes?
How much would that shift if you go to 99 or 3 sigma? Or
3 sigma confidence? So these two would stay, this is right around the peak. So they start to blow up at high L's. So you mean, how much would each one of these points change?
Well, the confidence, so would it go up?
Well, no. If you change it, if you increase the confidence, these would rescale up. I thought you were asking how many of these would remain. Not actually by that much. It's a fairly regular Gaussian. I mean, these are fairly standard 2 sigma limits. So I can't calculate in my head how much they'd go up, but they'd go up slightly. But there's an upper limit. So if we had a detection, then you're right. Then we'd want to probe deeper and see how it depends on the level of confidence that we assume.
What's the second source?
Yes, so I was going to get to this. This is gravitational lensing. So imagine the E-modes are laid down by the same physics that lays down temperature curves. So now you've got polarization vectors traveling through space and time. As they come close to galaxy clusters, though, a polarization pattern that looks like this might get rotated slightly if there's intervening matter, gravitating matter, which itself is asymmetrically distributed, as we think clusters and galaxies are asymmetrically distributed, and that can cause it to acquire a slight tilt. And it acquires a false B-mode signature. Not from gravitational waves. It's a true B-mode signal. And it is cosmological, but it's from gravitational lensing of the E-modes. So if I show this...
But you need to have, in some sense, a bias in one direction all along the line to get something like that.
Well,
I mean, if you get...
So this is shear. So if you look at galaxy clusters and you look at the shear of individual galaxies, there are patterns, which if you decompose them on the sky too, they use the same language, E and B. They would also potentially look for the signature as well. Not this signature. Okay? This actually arises slightly technical on how this is calculated, but if you do imagine that pattern with a random distribution, there will be some net residual B mode which will still arise. So you just take this pattern and put little random lenses which themselves have some asymmetry, some quadrupole moment to them in their center of mass.
So let me understand. This one here is sort of exaggerated, or
sorry?
What you,
So this is all B modes. So you go out, you have a fantastic angular precision. You can resolve down to a few arc minutes with your telescope. Okay. So this is high angular scales out here, 1/10 of a degree or 100th of a degree out in this direction over here. And you just make a map of the full sky in B modes. You look for the B mode content of the entire sky. There would be 2 contributions if inflation exists and created gravitational waves. If there are no gravitational waves from inflation, this term will be 0 and this will be off the map. But you will definitely have this lensing term, this lensing type of B mode, which doesn't tell you about gravitational waves, doesn't tell you about gravity other than lensing. It's gravitational lensing of the CMB.
But it's that you expect it to be that important. So
Yes.
above multiple of 100, it will completely mask
No.
the other effect.
Well, no. So this is for a signal of 10%. I'll show you down to the level which just a naive calculation could still detect it. Turns out it's about 2%. So you can lower this by a factor of 5 in R, which doesn't it scales as the square of this. So I'll show you those plots towards the end. But you don't become confusion dominated until you get below about 2% here, which corresponds to roughly an energy scale of inflation about 3 times 10 to the 15th GeV. Beyond, there is a limit below which you cannot detect.
And that's because you can look at the lower multiple.
Yes.
Yeah. Right. But what I'm saying is that in this particular example, above multiples of roughly 100,
Right.
it's completely, I mean, it sort of masks.
Above,
But of course, you have the lower
yes.
multiples that you can use.
Yeah, but that's the peak of the signal. And I've cut off on this plot, I've cut off the reionization signal. There's also a rescaling of the primordial gravitational wave background B mode at L of 7. Okay? And that's above the lensing scale unless the tensor to scale ratio is part of 10 to the 5th. Okay, so if you did an all sky measurement, you can measure the whole sky. There'll still be a little bump of primordial B modes corresponding to R of 100th of a percent or 1,000th of a percent. Okay, I didn't show it here because we can't measure from the ground. You can't measure below about this multiple about L40 or so. Yeah.
I think I have a fast question.
Sure.
The curve for the gravitational lensing, you must have a model for dark matter. I mean, many
Yes.
gravitational. So, is it correct to say that that curve on the right basically is using for dark matter?
Yes. Yes.
So
And
there is
neutrino mass. So there's another bit of physics, which I'm not going to talk about, but I'll explain just briefly later on. This traces P of K, the primordial power spectrum. So if there's dark matter in your model, yes, it will trace. This will be a dependent function on that. Now I'll tell you that I won't tell you who, but there is essentially an imminent publication on the way about a detection of gravitational lensing in the CMB. Okay, I'm not going to talk. It hasn't been released yet. There have been cross correlations which have detected evidence for gravitational lensing, but not purely using the CMB. Expect that this summer. Okay, but then that term is blind to several different effects, most notably parity violation because it's only temperature. They're only getting this from WMAP temperature map, and furthermore, it can't look for the neutrino mass for technical reasons, which we've written papers about, but we can talk afterwards about. Okay, so this is the state of the art in CMB B modes. Again, we've made factors of 2 orders of magnitude or more in just 6 years. Okay, looking for B modes, something that I was told by a very prominent theorist when I was doing my thesis that even the E modes were a waste of time. We should never do it. Okay. Okay, so this sets the stage. That's just plain old vanilla lambda CDM, inflationary cosmology, polarization, power spectrum. Now, last August, this team led by Jia, Junqing, Jia, and at that time, I guess now he's in Trieste, Italy, and Beirut at the same time. I don't know how that's possible.
It's via Beirut.
It's right, yeah, okay, so he's very hard about these.
It's not even more in via Beirut. We have moved.
Oh yeah?
Yeah, we have moved.
Okay. Well, this is actually from the published version, which was published 2 months ago. Okay. So this is a physics letters B article. They used our data, and essentially, you see down here this little likelihood curve. They're claiming at 68% confidence, 0.72 degree detection. They claim a 3 sigma detection of CPT violation. This is a published letter. Using most of the strength comes from our data. Okay. This black curve is just using the EE spectrum and the TE spectrum. This is using EB cross correlation, these forbidden cross correlations that we'll talk about. But the key point is that they claim a detection characterized by a rotation angle, a preferred orientation in space, which is Lorentz violating and parity violating. Singles out a preferred axis in the universe and an amount of rotation in that universe. Okay, and here's 0. So they're saying our data is inconsistent with 0 at recent. Okay, so this set us off to work because we didn't release this analysis, but we did release our data. And I remember back to many years ago, there was a publication, and I think it was on the front page of the New York Times in a small blurb in the late 90s, where there was a discussion using radio galaxies of a preferred handedness in the universe. This is the cartoon that was shown there, where galaxies had different handedness. This cartoon didn't make sense to me then. It doesn't make sense to me now. But they used radio data from Jake Shaft et al. From the 60s and 70s, and then some later data. And these two people claim that there is a handedness in the universe as well. And I haven't heard from either one of these in about that same elapsed amount of time. But anyway, this thing was studied at that time by several prominent theorists. What would happen if you did have a mass of a photon, or if you had a preferred helicity state independent of the model of physics that you choose that would give you this, a term that you add to the Lagrangian electromagnetism. It's very hard to see here, but I'll show it here. Okay, you modify the Lagrangian by adding a Chern-Simons term. So G and E dot B term, which would vanish if in standard Lorentz symmetries respectively. Well, this leads to a dispersion relationship, which instead of being omega equals k, instead you get this extra term here. And that leads to, when you take the square root for different values of chi and g, you get different phase velocities for left and right-handed circular polarized states. Which again, you can still get linear polarization if the two states propagate with different phase velocities. Okay? So now if you superimpose these, again, this is just restating the same thing, what happens is E, the electric field is still the same, but the B field gets rotated by 90 degrees or flipped. Okay? So parity, symmetry, and Lorentz invariance are violated. This is a little cartoon of what birefringence looks like in crystals. So there's a plane of polarization here. You can see that this is vertical. It's going up and down alternately. It's making this teal color, this light blue curve here. It's going into this cube, which is birefringent, and it's coming out rotated at this angle here. And that's because these two states have decomposed into counter-rotating circular states with different phase velocities in the medium. So what they're saying, Gia and others, and many others have looked at this, is that certain terms, perhaps an axion, photon mass, other things, can produce a rotation of the plane of linear polarization. And what happens if that's true? Well, nothing happens to temperature. Temperature is a scalar. It's not affected by the polarization. But the other terms that involve any form of polarization do change. There's 6 possible polarization power spectra. TT, obviously, TB, cross-correlation of T and B. This vanishes without things like parity violation. This vanishes, EB, electric type with magnetic type, as Joao described the other day. And then TE, EE, and BB, these exist as do these. So standard lambda CDM just involves this, this, and this, and this. And this is what was sensitive to realization. Now E and B, the new EE and BB, involve a quadratic function of the angle, and they're not sensitive to the sign of alpha. So typically we only look at these two terms here, EB and TB, and these are forbidden. These don't exist unless you have things like cosmic birefringence. And this is what Gia et al. Used to detect, or claim a detection of parity violation. Okay, so these exist in standard, they're parity even. These are parity odd. Even though B is parity odd, BB is parity even. So this power spectrum we can look for, and this is what we set the most stringent upper limits on. Okay? So if there's a magnetic field, parity violation or Lorentz symmetry invariance breaking, they do not vanish, and so this is what people typically look for when they're trying to set limits on this. And many groups have set limits on this. This is the first detection claim. Okay, here's what their data, they use our data from the quad polarimeter, which is a sister experiment at the South Pole, boomerang data. They also use WMAP data, and WMAP in Komatsu et al., one of the most recent, every time they release a paper, they release a non-detection of this effect. So it's not like it's so fringe. People are looking into this as well. Okay, here's our data in red. This is the EB forbidden spectrum. This is the TB forbidden spectrum. So they're clearly using the TB. And I'll come back to these slides here. This is just a blow-up of what you actually look like. But if you did have a rotation of 2.6 degrees, what you would get for BB, you'd get a spurious BB that would look like a rescaled version of EB. Okay, you still have the lensing signal here, but it would be comparable or larger than the lensing signal. So you get a BB that you could not distinguish from lensing, because it would be bigger than lensing, but it would have these acoustic peaks superimposed, because this is directly lensed, rotated E modes into B modes.
I don't understand why this is CPT violating. I understand why it's CP violating.
Oh, it's CP violet. That is the title at the top. Yeah.
Yeah, but they were claiming CPT violation.
I think they combine them. They don't mention T at all. They mention C and P. They mention that and Lawrence violation.
I mean, but CPT is much more sacred than CP.
Well, still, if CP is violated, right? I mean, we know that CP is violated.
Yeah, we see
But-
it in the most.
Okay.
No, what confuses me is that if I am sure I have a CPT violation, then I do have for sure a Lawrence violation. It's the way out.
Okay.
But if I just a CP violation, I don't believe that I should have a Lawrence violation. So I'm confused a little bit because before you were saying, I mean, what they're saying, does it mean that there is a Lawrence violation or not from their point of view?
Does it mean that there's Lorentz violation?
Yeah.
Yes, I think so. I think so.
Okay,
Because you have a
not-
preferred axis in the universe. You have a preferred axis, a longitudinal axis in the universe about which this rotates.
I can have Lawrence equal in the CP violation.
You can or you can't.
If I say it was CPT, yes.
Okay. I'm not an expert in
You
that.
see, CPT violation implies Lawrence violation. It's not through the reverse.
Oh, the converse.
But still, if you can violate CP without violating CPT.
Right, that's what we have, right?
And so now you so the data actually are saying that CP is violated.
Yes.
They are not proving that CPT is violated.
But in the electromagnetic sector, in the pure electromagnetism sector, arising from this model of the universe has a refraction index different for left and right circular polarized state. Whatever it is, it would be remarkable. It's not true. So hold off on the assault because I don't want to spoil the punchline. Anyway, we built this machine to go after this difficult problem of detecting gravitational wave background, but we see it has utility other than that. This is the team. BICEP stands for Bolometric Imaging of Cosmic Extragalactic Polarization. We built it with collaborators at JPL Caltech and Berkeley. This is the core of the team. It's a National Science Foundation sponsored project. It's very hard to see in this image here. This was taken in the lab before we went to the South Pole. It's a refracting telescope. It's the first refractor used in cosmology in over 100 years since Yerkes. But a refractor is remarkably clean. You know, polarization scattering off of metal can be acquired from an unpolarized source. So when I wanted to design a very clean telescope, I knew a refractor would be at least one of the first choices. In addition, since the signal is at L of 100 or so, which is 2 degrees on the sky, we don't need very high resolution. So the refracting telescope, it only has a diameter of 30 centimeters. We don't have a 10-meter telescope. We don't need a 10-meter telescope to go after just the gravitational wave background. Okay? It's enabled by detectors called polarization-sensitive bolometers. Here's a cartoon. A photon comes in, excites this membrane or this membrane, and these are about 25 millimeters across, heats up this membrane, which is cooled to 0.25 Kelvin, heats it up by a few millikelvin. We measure that as a change in the resistance of this thermistor. We read out that thermistor. We make an array of these things here, and if you were a photon traveling from the beginning of time, this would be the last thing you ever saw, and you choose which one of these pixels you end up in. Now, this is not a megapixel camera. It's not an iPhone. It's like a milli iPhone or something, right? We have 100 detectors, two per feed horn that you see here. And Lee's not here, but this is the reason I was saying yesterday that we only have a finite amount of real estate that you can feed with the size of the wavelengths that we're dealing with. We can build things as small as we like. I'll show you a lot of advanced technologies later. Anyway, we have 2 different colors, 150 gigahertz. Actually, we have 3, 150 gigahertz, 100 gigahertz. And these are 2 little guys that are particularly important for foregrounds. These are 220 gigahertz pixels. Okay? And this is the first time we built an experiment to just go after the gravitational wave background. Okay, so BICEP we located at the South Pole. The South Pole is the driest desert on Earth, drier than the Sahara. A few hundred microns of precipitable water vapor between us and outer space. Water absorbs microwaves. We built it here. It's a beautiful laboratory. The scenery is not much, but you can come to Sweden if you want good scenery. Okay, so we put the telescope, that refractor goes in here, and this is just a ground screen that screens out the Antarctic surroundings. This is the construction photos. That building used to have another little building. We scraped it off. This is the surrounding area around there. There's several other experiments here. Ice Cube is over here. It's one of our neighbors. It actually surrounds much of this. This is Daisy. This is the South Pole Station where we sleep, and beautiful accommodations, actually. The telescope was lowered in. Got lowered in there. We put the receiver. This is cooled to 4 Kelvin at first. Then it's cooled to 0.25 Kelvin. Okay, this is all of us standing around after we got it in. It was working. The sun is up 24 hours a day from September basically until March, and then it's a long cold night. We have one person that watches the experiment from when we all leave in March, or in February actually, till November. And we just told him, just work for one night. That's all we want. And he felt.
I mean, there is a single guy.
Single guy.
All the Antarctic winter.
Yes, there are 45 of them. 45 people spend the time there. Currently, our winter over is Stefan Richter. He's a German, former German infantry soldier. He's been there. He's been there 6 straight years.
Oh, wow.
He comes home for 2 months to Christchurch. Christchurch is where he goes in the first summer, and his permanent mailing address is the South Pole. This is our postcard. It's very hard to see. It's from the first microwave from the last day of December of 2005. So after this, we got visitors came in and wanted to see it. This is John McCain. He visited it. Okay. He wants to detect inflation. Okay, there he is. It's very hard to see, but he's taking a nap. And I think he's dreaming about finding a running mate from somewhere cold, and that's why he came to the South Pole. But it was really the other side of the planet. Anyway, these are the maps that we made of the microwave background. These are the most deepest maps, most sensitive maps made at these frequencies in this type of measurement. So we have maps of temperature at these 2 frequencies, 100 and 150. We can average them, and we can difference them, and that's a powerful systematic check. You should get pure noise, and we do. This is a map of E mode, 100 gigahertz map, and 150 gigahertz map. Difference them, we get pure noise. This looks different than this. B mode, the sum, the average signal, looks the same as the noise. That's a null detection. Okay, we do it much more sophisticated, but this is kind of in cartoons. This is real data that we've measured. That's the most sensitive ever done. These are the power spectra, and we'll go through what they actually look like. We do release all the power spectra, including TB and EB. Okay? And we knew that there were systematics embedded in them, but we didn't care. We're not looking for that at first. We didn't dig down. And it turns out that systematic effects can masquerade as polarization effects. And I'm going to review just one of them, which is if your 2 telescope beams for X polarization and Y polarization have different amounts of ellipticity to their beams, they're usually circular Gaussian shape like this guy is, but if they have different amounts and then you difference them, you get this cloverleaf pattern, which looks like a false polarization. I won't go through the actual details of it. You can get spurious signals depending on the amount of mismatch of the 2 beams. And the only point I want to make is that we designed BICEP to go after BB. Now imagine you have a leakage of temperature, which is huge, 2.7 Kelvin, to B mode. And we parameterize that by omega. Well, BB will go like omega squared, but TB will go only like omega. So that means if you design it for BB, it may not be good enough for measuring TB. And G et al. Overlooked that. Okay? I'm going to skip these things, this slide here. Back to their data. They ignored that. They just took our data, put it through a Monte Carlo pipeline, got out error bars and predictions, and here's what they show. They claim a detection, as I said, 3 sigma, rotation of about 2.5 degrees. What my group has done is taken our data, analyzed it, and we found that what they actually got were 2 different power spectra. One for 150 gigahertz, where we do show some spurious polarization, spurious rotation, which we think is from calibration, and we can treat that. But we don't see it, so...
How you know it's spurious?
Oh, because we calibrated it out. We just didn't calibrate it for BB, because it doesn't affect us. We can make an error as large as 10 degrees in this type of calibration and still measure BB at 10% tensor to scale ratio. So we just said we ignored it. But if we go back and correct it with our calibrators, I skipped over the calibration slide. We do correct that. We can correct this. It doesn't improve our BB limits, though. So we are going to release that when we release this refutation of their analysis. But the point I want to make is that we have 150 gigahertz data. It shows a systematic shift, but the systematic shift comes from 2 places. There's T and B. The T map that we used had issues. We're a polarimeter, not designed to go after temperature anisotropy specifically. We do measure the temperature anisotropy. But this leakage, we did not look into constraining this. So it's not surprising that they could get this. Not from the rotation of the polarization plane necessarily, which we can rule out, as I said, using our calibration, but from leakage of the temperature because of these beam effects. Okay, so you see a signal from leakage of temperature, which we didn't care about because we're a polarimeter. But you don't see it at 100 gigahertz. 100 gigahertz is completely consistent with 0. And look, if you average the error bar, if you average the mean values at 100 with that at 150, so 5 average with 0, you get 2.5, negative 2.5. Okay? So that's exactly what they did. And that is our justification that this result has to be wrong. If you expect a cosmic birefringence signal, it should be the same at all frequencies, electromagnetic frequencies. Okay? So it should be the same at all frequencies. It's clearly not the same at 100 and 150. That's one clue that this result was completely wrong.
Strictly speaking, what you just said is not true.
Say
You
again?
can have models.
Sure, but not their model. They don't have any color.
They have analyzing data. I mean, if the data may tell you that the model you have to look for explaining it is a model where birefringence is frequency dependent.
Okay, but then they wouldn't see it at 90. They don't. WMAP doesn't see it at 100 gigahertz. We don't see it at 100 gigahertz. We only see it at 150 gigahertz.
No, exactly.
And Quad doesn't see it at 150
You
gigahertz.
may have it that is present. That has a dependence on frequency, which is complicated enough that you see it.
But that would be pretty fine tuning. I mean, first of all, it'd be pretty fine
For
tuning.
example, the models where you have just to give you you can have models with dimension 5 ones by the Fluid operator, which have the cube over M, over M Planck. Those have normally they violate.
Right. Okay, that wouldn't be the first thing I look at. I would be looking at things in the instrument, like refractive indices that scale much more strongly with frequency.
What I'm saying is that model-wise is not so incredible that you can have birefringence, which is very well constrained, you may say, by other things. And so I think that it would be difficult to have it so important that this energy and not see it.
This is not their main refutation. This is just saying this is a clue that they could be wrong.
Right.
The point is that you can have frequency dependence, but not so drastic that you see it at 150 and you don't see it at 100. What?
It would be how finely tuned was that?
As one I just said, no, because it's generally smooth.
Right.
It's a power law, but it's a model.
Because
But
we have to have
you
a strong power law.
can have a kind of step function, something smooth.
At least
You have to be careful to say that it's impossible to have a
Not
birefringence.
impossible, but it would be a bit.
It's contrived. So is having.
Natural.
Why would set that frequency scale to be so sharp between 100 and 150 that you get this 5 degrees?
But what if you, actually, we have a paper with Alessandro Vecchioli studying this possibility of birefringence with energy dependence, which you find it's quantized space-time actually is very difficult to get rid of it. We try, but it's very difficult to get rid of it.
But I understood that those are very high frequencies, optical frequencies. I mean, they correspond to TeV.
They scale with energy. You expect them to be stronger at higher energies and much weaker at lower energies. But if you work out the numbers, because of the long propagation time of the CMB,
Sure.
that is a big amplifier. So we actually have a paper where the numbers could go down. Certainly from 100 hertz to 150 hertz, it's pretty short range to gain a huge effect. But it should be taken into account. I mean, a quadratic dependence on energy, for example, is very natural. And to go from 100 to 150, you would mean you expect double the effect.
Possibly. But let me continue, because
If you see
we do have data at 150 also from our sister experiment Quad, which showed no detection.
That's
But this is more of a cautionary tale for theorists. Okay, that in addition, you should use the power spectra that we publish. That's what we put them there for. But you should consult with us. You should say, why did you not use your temperature? Why did you not further refine your temperature beyond this? Because we do a full analysis in this paper that we're working to submit soon that shows that even from the existing data, they didn't have the data bifurcated, but they didn't ask us about it. They also didn't look into the systematics from the beam rotation and from beam mismatch, which we only limited to the tensor to scalar ratio. They didn't look into that, and you need a very small amount of that to get this type of effect too. But it's correctable. They didn't ask. So all I'm saying is that that's a very dangerous proposition to go for. Okay. I should also say that if there is a strong dependence, WMAP doesn't have a 100 gigahertz channel, it has a 90 gigahertz channel. Okay? Which we can distinguish between their center band and our center band with very high accuracy. So they're totally different instruments. One's in space, one's using bolometers. Okay? The bottom line is that they don't see it at 100 gigahertz. Okay, this is just showing the different combinations. We don't see it if instead of looking at 100 gigahertz temperature correlated with 150 gigahertz B mode, if we switch that and we do 100 gigahertz B mode correlated with 150 gigahertz temperature, we see no effect. So remember, you have two different slots, T and D, but you have two different frequencies. So there's 4 different permutations that you can arrange just from that. We don't see it in 3 of the 4 of those. They put the one where you do see it. So that would be hard to explain even from a very strong frequency dependence, because you should see the same. Okay, this is Quad's data. Quad shows no evidence for this effect. They show 0 as their best fit. WMAP down here shows delta alpha. This is all their data combined is consistent with 0 at 90 gigahertz. Okay, we have a paper that we wrote 2 years ago about how these effects could masquerade as cosmic birefringence. They didn't cite it in the original paper, and now they cited it. Okay. And the last thing I want to talk about is, and then these are relationships that we think we could probe with respect to the models that Joao talked about the other day, just putting our data on his power spectrum here, where he shows that the power spectrum of spurious TB from chiral gravity could be larger than the BB signal, okay, where the EB signal will be small. Okay? I'm going to go through this really quickly. We're upgrading BICEP to make it more look like a CCD camera. It's very hard to see this. We've now included 10 times more detectors in the focal plane, same telescope at the South Pole. Even harder to see this. We call this BICEP 2. It's about 8 times more sensitive than BICEP 1, or has 8 times more detectors effectively than BICEP 1 when you take everything into account. Their detectors look like this. These are slots of superconducting material. These are slots in the superconducting ground plane. These are little slot lines that feed to kilometers on isolated little islands. This is all 1 pixel, okay, and each pixel is about 12 millimeters across. Okay. Here's a blow-up of it. That's the island. These are filters that separate out the electromagnetic frequencies. This is a meander that causes this island to heat up. It's transduced by a superconducting sensor near its superconducting to normal transition. Very sensitive thermistors. Lastly, I want to talk about polar bear, which we just fielded the last few months in California. This is a huge telescope, 3.5 meter primary. This is going after the primordial B modes and the lensing, so you need large apertures to get high angular resolution. We're now going to move to Chile in the Atacama Desert near the almond dishes in about 3 months. So I'll be moving down there. And we're going to put it inside a huge screen to keep out like you saw in BICEP. It uses a slightly different type of bolometric detector, but it's also superconducting. A very large cryostat, little tiny microscopic lenses, little tiny lenses of silicon, and then pack these arrays. We pack 7 of these arrays. We get 1,274 detectors. And this is what we can do with polar bear. We can go after the E modes, calculate all in one experiment the entire range of interest for E modes. We can characterize lensing very accurately. This model can only shift on this curve by about the width of the tip of the pointer. So this will allow us to construct estimators of the lensing effect. Here's the gravitational wave B mode for our 10%. This is that 2% effect down here. Okay, and would be right here. This combined with this, we can actually separate out this little hump from this if this were going down to 0. This is a double logarithmic scale, so it's a little hard to see that. But statistically, we can resolve a tensor to scalar ratio of 2.5%, which is about what we would think is the lowest that we can detect, comparable to what the gut scale is in some models.
What is Planck going to be?
Planck won't detect. It will detect the E modes. It may detect the lensing and temperature very well. We have our doubts. One of the last conversations I had with Andrew Lang is that they would not be able to detect these B modes, but it's dangerous to quote people posthumously. But the bottom line is they were polarization sensitivity is minimal compared to things that have dedicated polarimeters in space. Our mirror is much bigger than theirs, 3 times bigger almost, 2.5 times bigger. And we have of order 12 times more detectors. And they're equally sensitive in that sense. Plus, Planck spreads its time out over the whole sky. We focus on the cleanest 1 or 2% of the sky. No foreground. And lastly, we think with polar bear and upgrades to polar bear, that we can get a precision on alpha of just a few arc minutes. So remember, BICEP is way up here at several degrees. If you believe the width of the distribution is characteristic of our constraining ability, we could constrain it to within a degree or so, which would be up here. With polar bear, we can go at least down to about 2 arc minute ability to constrain. And that will be powerful both for cosmic birefringence and for possible chiral gravity. So, last slide, I've said all this, so I'll take any more questions that you guys have. But the future looks quite good for being able to test not just inflationary physics, but these things beyond the gut scale. Thanks.
So, questions?
Can you say a little bit more about the cosmic violation, the gravitational one?
Oh, the gravitational? Yeah, so my understanding from my conversations with Joao and Lee is that this effect is also coupling or emphasizing a propensity of left-handed versus right-handed gravitational waves. These are primordial gravitational waves. And so these will manifest themselves in a different type of correlation. There'll be a temperature signature as well, but that would be way degenerate with just the CMB temperature anisotropy as it is. If this is indeed true, the only problem with this, as I see it, is that it depends on 2 unknown parameters: the chirality parameter, which has to come from some physical motivation to please me, and the tensor to scalar ratio, which could be very low. This is showing 10% tensor to scalar ratio, so the same plots I showed with respect to bicep, but it's showing a chirality parameter of 10. But I need to develop more of a feel for what that means. But I believe that it could already limit value combinations of gamma and R with bicep data. Just no one has done that.
So can we call you when we want to if we active and you said you said the Chinese theorists did not get advice from the experimentalists.
Yes.
Which of course is always desirable. But so do we get to call you now?
Sure. Email is preferred. My iPhone charges too much for international calls.
I'll send you an email when I have my next thing.
Yeah, please share it. Yeah. We always like help with analyzing time-ordered data.
Including these and all experiments that you know of, what is the lowest tensor to scalar ratio we would be ever sensitive to?
Well, I think in terms of realistic experiments for the next decade, something at the percent level, a few percent level, as I'm showing with polar bear and bicep 2, the main target and the target that was set by United States funding agencies for proposals for things like NASA's next satellite was a tensor to scalar ratio of about 1%. Okay, again, that corresponds to mid 10 to the 15th GeV energy scale of inflation. But a satellite cannot have the resolution of a ground-based instrument, so it's kind of an interesting situation. We may be in a situation where we launch a satellite like BICEP into space, which is what we propose to do actually, an array of these BICEP small refracting telescopes into space, and then we follow up with big telescopes on the ground like polar bear, with an array of big telescopes on the ground, which could be done for, the combination of that could be done for about 10% of the LHC cost, $1 billion roughly. These experiments are cheap, I mean, they're a few $1 million, and they employ tens of people. Yeah?
Could you discuss on how we compare the advantages? I mean, I can see the advantages, but also taking into account the budget cost between having an experiment like CMB poll as compared to having many of these ground-based experiments.
Yeah.
So what are the advantages and the sensitivity that you expect? And also perhaps also mention a little bit the sensitivities that you expect, how that would compare with the sensitivity for primordial gravitational waves, the energy up to what kind of so up to what energy of inflation you would be sensitive.
Yes. So to answer the first question.
Scale of inflation you would be sensitive.
Yeah. To answer the first question first. So these experiments, as I said, these are quite cost-effective to ground-based experiments. The space-based experiments, as soon as you talk about going into space, we did 2 missions. One was a full comprehensive mission. One was a small mission. The small mission was $800 million US. The expensive one was 1.5, and then we stopped counting. Billion US. So those are very expensive. And those may be the only way that you can get the very full sky coverage that you need to get down to, as WMAP showed, to detect the amplitude of E modes from inflation, from reionization. There's a B mode signature down there as well. That would be our last and perhaps only hope if the tension to scalar ratio is below about a part in 10 to the 4th or 10 to the 5th, 100th to 1,000th of a percent. So that is probably the ultimate limit, just confusion from gravitational lensing, as we brought up earlier. Okay, so that requires full sky coverage. You can only get that from a balloon, and there is a balloon called Spider at Princeton and Caltech, and it's an array of biceps on a long duration balloon. But those are very risky. The satellite experiment could be done, as I said, for several hundred million US, and that could get the full sky coverage. You still would need to follow up for two reasons. To get for the lensing signature and these parity violating signatures, which peak at high L, small angles, and for foregrounds. You need to go deep and remove foregrounds with the ground with high resolution to build models. And then you can subtract that. Planck will give us a lot of information as well. And Planck should detect, everything that's interesting about the E mode, Planck will clean up. WMAP didn't. WMAP has very few detections. The second question you were saying is, what is the ultimate limit? So that fraction of 1,000th of a percent corresponds to high, because the dependence on energy scale inflation is to the fourth power. So you get a quartic function. So that only gives you about a window between, say, 10 to the 14th GeV and 10 to the 16th GeV. We're currently at about 5 times 10 to the 16th GeV with bicep alone. You combine it with temperature, because there is a temperature signal. You can lower it a little bit.
So 10 to 14 is the lowest you can get?
Yeah, several times 10 to the 14th. Yeah. With kind of, without going to heroic efforts to remove lensing, without requiring an all-sky survey of lensing, for example.
Oh, 10 to the 14 would be with ground based.
Well, it would be a combination of ground and space.
And space.
Yes.
So that's the ultimate thing with
that's pretty much accepted as the ultimate limit. R of the 10 to the 4 minus 1. Okay.